What if everything you've ever touched, seen, or felt, including you, is nothing more than information projected onto the walls of reality, like a cosmic video game running on hardware we can't even see? Think about the last time you stared up at the night sky from your backyard, maybe after watching an Apollo documentary or following a NASA live stream, and felt that gut punch feeling that something about this universe is almost too perfect, too precise, too mathematically clean to be entirely real. Scientists aren't just asking that question anymore. They're finding answers, and those answers are genuinely unsettling. Hey, welcome in. I'm Matt, and this is Astro Matt, where we take the biggest, most brain-bending ideas in space and physics and break them down in a way that actually makes sense. Today we're diving into 10 discoveries that have led some of the sharpest minds on the planet to seriously consider that our universe might not be what it appears to be. Not science fiction, not philosophy, real data, real experiments, real implications. Stick with me all the way to the end, because these 10 points build on each other, and the final one might just change the way you look at everything around you. And if you're new here and you love this kind of clear, curiosity-driven exploration of space and physics, go ahead and hit subscribe. We do this all the time on Astro Matt, and trust me, you don't want to miss what's coming next. Let's start with a question that sounds like it belongs in a movie, but is actually being debated in the most serious physics departments in America right now. What if the universe isn't a place? What if it's a process? You've probably heard of the simulation hypothesis. Most people connect it to science fiction, The Matrix, video games, Hollywood. But here's what's wild. The version that physicists are actually discussing isn't science fiction at all. It's rooted in real mathematics, real cosmology, and some genuinely strange discoveries about the nature of reality that have come out of American research institutions over the past few decades. Here's the core idea. When you play a video game, the computer running it doesn't render the entire world at once. It only processes what the player can currently see. Everything else exists as potential, as data waiting to be called up. Now here's where it gets interesting. Quantum mechanics, the most tested and accurate theory in the history of science, tells us something almost identical about our universe. Particles don't have definite positions, definite speeds, or even definite existence until they are measured or observed. Before that moment, they exist as a wave of probabilities, pure potential, just like unrendered game data. That's not a metaphor. That's what the experiments show. Physicists at institutions like Caltech, MIT, and Fermilab have spent decades probing this behavior, and the results keep pointing to the same uncomfortable conclusion. Reality, at its deepest level, is not a collection of solid objects sitting in space. It behaves more like information, responding to observation, collapsing into definite form only when something interacts with it. And when you combine that with the fact that our universe appears to run on mathematics so clean, so consistent, and so compressible that a handful of equations can describe billions of light-years of cosmic behavior, the simulation hypothesis stops sounding crazy. It starts sounding like a serious scientific question that NASA space discovery data and cutting-edge universe-explained research are pushing closer and closer to the surface. We're not saying the universe is fake. We're saying it may be fundamentally different from what our senses tell us, and the science facts backing that up are only getting harder to ignore. Now, if reality is more like information than matter, the next question is obvious. Where is that information stored, and what does it look like? Okay, so we've established that reality might be made of information rather than solid matter. But here's where things get truly cinematic. What if our entire three-dimensional universe, every galaxy, every black hole, every mountain range, every city in America, is actually a projection? Not a metaphor for a projection. A literal, physical projection from a two-dimensional surface surrounding the cosmos. This is called the holographic principle, and it is one of the most stunning and legitimately supported ideas in modern physics. Here's an analogy that might help. Think about a credit card hologram. You know, the little shiny sticker on the front of your Visa or MasterCard? That flat two-dimensional surface contains encoded information that your eye reads as a three-dimensional image. depth, shape, dimension, all of it generated from a flat sheet. Now scale that up to the size of the entire observable universe, and you're starting to approach what theoretical physicists are actually proposing. The idea was first developed seriously by physicists Jacob Bekenstein and Stephen Hawking while studying black holes, one of the greatest space discovery moments in modern science. They found something deeply strange. The information content of a black hole isn't stored in its volume. It's encoded on its surface area, its two-dimensional boundary. That was the first major clue that in our universe, three-dimensional space might be less fundamental than it appears. Then in the late 1990s, physicist Juan Maldacena developed what's called the ADS-CFT correspondence, a mathematical framework showing that a universe with gravity operating in three dimensions can be perfectly described by a theory with no gravity operating on its two-dimensional boundary. Like a perfect translation between two completely different realities, same information, different dimensions. NASA's Fermi Gamma Ray Space Telescope has since contributed to this picture by scanning the universe for signs of pixelation or granularity at the smallest scales, essentially looking for the seams in the projection. The universe explained through this lens stops being a stage and starts being a screen. And if our three-dimensional reality is a projection of two-dimensional information, one question becomes unavoidable. Who or what is doing the projecting, and why does it only become real the moment something looks at it? So reality is a projection, and it only becomes real when something looks at it. That second part, that's not just a poetic idea. That is a laboratory-verified, experimentally confirmed, science fact that has been rattling the foundations of physics for nearly a century. Let's talk about the strangest experiment in the history of science. It's called the double-slit experiment, and it was refined and confirmed by American physicists at institutions like Caltech and the National Institute of Standards and Technology. Here's what happens. You fire individual particles, electrons, photons, even atoms, at a barrier with two narrow slits cut into it. Behind the barrier is a detector screen. Simple setup. What you'd expect is two bands of impact marks, one behind each slit. What you actually get is something that should be impossible. You get an interference pattern. Dozens of alternating bands, light and dark, spread across the screen. The kind of pattern you only get when waves overlap and interfere with each other. But you fired individual particles, one at a time. Each particle somehow went through both slits simultaneously, interfered with itself, and landed in a pattern that only makes sense if it traveled as a wave of pure probability across the entire space. Now here is where the universe explained gets genuinely uncomfortable. The moment scientists added a detector to find out which slit the particle actually went through, just by watching, the interference pattern vanished. Completely. The particle stopped behaving like a wave and started behaving like a normal solid object going through one slit. The act of observation collapsed the wave of probability into a single, definite reality. Think about that in everyday American terms. Imagine your morning commute only becomes a specific route the moment you look at the road. Before you check, every possible path exists simultaneously. That's not a metaphor for quantum mechanics. That is quantum mechanics. Scaled down to the level of the particles everything around you is made of. NASA Space Discovery Research and quantum physics labs across the country have replicated and extended this experiment hundreds of times with increasingly large and complex particles. The result never changes. Reality, at its most fundamental level, is indefinite until observed. It exists as potential, as information, as probability, and only firms up into something concrete when the universe, in some sense, takes notice. Which raises a question that connects directly to our next discovery. If the universe requires observation to become real, what happens when we zoom all the way in and ask how small reality actually gets? So reality only becomes definite when observed. Particles exist as pure probability until something interacts with them. The universe behaves like information. All of that is strange enough, but now let's zoom out, way out, to the scale of the entire cosmos. Because when you look at the universe as a whole, you find something that many physicists consider the most unsettling science fact of all. The universe looks like it was built to order. Not metaphorically, mathematically. There are numbers baked into the fabric of reality called fundamental constants: the strength of gravity, the mass of an electron, the speed of light, the force that holds atomic nuclei together. These numbers don't come from any theory. They can't be calculated or predicted. They simply are what they are. And here is what makes this one of the most debated space discovery topics in modern cosmology. If any one of these constants were even slightly different, not dramatically different, just a tiny fraction off in either direction, the universe as we know it could not exist. Let's make this feel real with an American analogy. Imagine the universe is a combination lock with 100 dials. Each dial has billions of possible settings. Every single dial has to land on exactly the right number for the lock to open, for stars to form, for chemistry to work, for planets to exist, for life to emerge. The odds of that happening by pure chance are so incomprehensibly small that calling it a coincidence starts to feel almost intellectually dishonest. Physicists at Princeton, the University of Chicago, and research teams connected to NASA space programs have studied this fine-tuning problem for decades. Some propose the multiverse, the idea that infinite universes exist with different constants, and we simply find ourselves in the one that worked. That's a legitimate scientific hypothesis. But here's what's interesting. The multiverse solution doesn't actually eliminate the fine-tuning problem. It relocates it. You still need a system capable of generating universes with precisely variable constants. You still need the machinery to be set up just right. And when you step back and look at the universe explained through the lens of information theory, the fine-tuning starts to look less like a lucky accident and more like deliberate parameters. Like values entered into a system before it was switched on. Like code. Every programmer knows that before a simulation runs, someone has to set the initial conditions. And what we're about to look at next suggests the universe may have a resolution limit that only makes sense if those initial conditions were set by something operating at a scale we can barely imagine. So the universe has precisely tuned constants that look like programmed parameters. Reality only firms up when observed. Everything might be a holographic projection of two-dimensional information. And quantum mechanics tells us that beneath the surface, the cosmos runs on probability and potential rather than solid matter. Now we go deeper, all the way down to the smallest possible scale of reality. And what we find there might be the most quietly explosive science fact in this entire video. Reality appears to have a pixel size. That smallest unit is called the Planck length. It was calculated by physicist Max Planck and later developed extensively by American researchers at institutions including Fermilab and the University of Chicago. The Planck length is incomprehensibly small, so small that if an atom were scaled up to the size of the entire observable universe, the Planck length would still be smaller than that atom. We are talking about the absolute basement of physical reality, the smallest distance that can meaningfully exist within the known laws of physics. Here is why that matters enormously to this conversation. In any digital system, a video game, a computer simulation, a rendered environment, there is always a minimum resolution, a smallest possible unit of space that the system can represent. Below that threshold, the concept of position simply doesn't exist within that system. The grid runs out, and the Planck length behaves exactly like that. Below it, according to our best current physics, space itself loses meaning. Distance stops being a useful concept. The fabric of reality hits its lowest resolution. Think about it this way. When you watch a 4K video on your TV, it looks perfectly smooth and continuous. But zoom in far enough on any screen, and you hit the pixel, the smallest unit, the indivisible point where the image breaks down into discrete squares of information. The universe, zoomed into the Planck scale, does something remarkably similar. NASA's Fermi Gamma Ray Space Telescope was actually used in a landmark American space discovery to probe this idea directly, scanning high-energy light that had traveled billions of light-years across the cosmos. looking for tiny distortions that would indicate the universe has granularity at the smallest scales. The results were tantalizing. Space appeared smoother than some models predicted, but the investigation itself confirmed that this is now a serious, testable scientific question rather than pure speculation. Digital physics, a field developed significantly by American physicist John Archibald Wheeler at Princeton, who famously proposed that information is the most fundamental ingredient of reality, with his phrase, "it from bit," suggests that space, time, and matter are all emergent properties of something deeper, something computational, something that processes information according to rules, at a resolution defined by the Planck scale, in a cosmos that increasingly resembles a universe explained not by classical solid matter, but by the logic of a system running on the deepest possible code. And when you line up everything we've covered, observation collapsing reality, holographic encoding of information, fine-tuned constants, and a universe with a minimum pixel size, the picture that emerges leads us directly to the discoveries that push this idea furthest, into territory where physics, cosmology, and the deepest questions about existence itself begin to converge. Let's take a breath and think about what we've actually covered today. We started with the simulation hypothesis, not as science fiction, but as a legitimate framework being explored in the most serious physics departments in America. We discovered that quantum mechanics, the most accurate and tested theory in the history of science, tells us that reality at its most fundamental level doesn't exist in a definite form until it is observed. Particles live as waves of pure probability, collapsing into something concrete only when the universe takes notice. That alone should stop you in your tracks. Then we found that the universe appears to be holographic, that the three-dimensional world we move through every day may be a projection of two-dimensional information encoded on a cosmic boundary, the same principle discovered while studying black holes by physicists building on decades of American scientific research. And finally, we zoomed all the way down to the Planck scale and found what looks unmistakably like a pixel size, a minimum resolution below which space itself loses meaning, exactly as you would expect in any system that is fundamentally computational rather than physical. 3 ideas. Observable reality that requires a witness, a holographic cosmos encoded like data, a universe with a resolution limit, and together they point towards something that even the most cautious physicists are now willing to say out loud, that the nature of reality is far stranger, far more layered, and far less solid than anything our senses have ever suggested. Here in America, NASA's next generation of space exploration missions, from the Nancy Grace Roman Space Telescope to future probes of the cosmic microwave background, are going to keep pushing at exactly these universe mystery questions. The science explained in this video isn't settled, it's alive, it's moving, and the answers, when they come, are going to reshape everything. Now here's the thought I want to leave you with. Every civilization throughout human history looked at the night sky and asked what it was made of. We asked the same question, pointed our best instruments at the smallest possible scales and the largest possible distances, and the universe answered back with something nobody expected. It answered with information, with mathematics, with behavior that looks less like a collection of objects and more like a process being computed in real time. You are not just a person watching a space video. According to the deepest physics we currently have, you are a pattern of information in a cosmos that may only be real because something, somehow, is observing it. That is not a small idea. That is the biggest NASA discovery-adjacent thought that modern science has ever produced. And we are only just beginning to understand it. If this kind of clear, wonder-driven exploration of space and physics is what you come to YouTube for, then Astromat is exactly where you need to be. Hit that subscribe button right now and join this community of genuinely curious minds. New videos drop every single week here on Astromat, covering the biggest questions in space exploration, cosmology, and the science explained with the clarity and depth that you deserve. The universe is stranger than we imagined. Let's keep exploring it together. Hey, thank you so much for watching this one all the way through. It genuinely means a lot. The fact that you now know reality itself may have a pixel size, a minimum resolution at the Planck scale, where space simply runs out. That is not a small thing to carry around. That is the kind of idea that changes how you see everything. And as NASA keeps pushing deeper into the cosmos with the next generation of missions, questions like these aren't staying in the philosophy classroom anymore. They're moving into the lab, into the telescope, into the science that's going to define America's future in space. I love exploring this stuff with you. Honestly, there is nowhere else I'd rather be than right here, digging into the most mind-blowing corners of the universe together. I'll see you in the next one.